What's up? I'm Vin, and today I want to show you how to write a Taylor series. So this is the formula that we're going to need. And first up here, we're going to find the Taylor series expansion for f of x equals 1 over x plus 2 about x equals 3. And then we're going to write the series in sigma notation. So when you hear the phrase about x equals 3, that's telling you the center of the series. And that's the a value in the formula. So here we could say that a is equal to 3. Now, when you use this formula, I highly recommend that you start off with the stuff on the right here. So the first thing I would do is plug in a equals 3 to the right side. And that's going to give us, we're going to have f of x is equal to, we'll have f of 3. And then next we'll have plus, we'll have f prime of 3 times x minus 3. And then next we'll have f double prime of 3. And then we're multiplying by x minus 3 squared over 2 factorial. So for this part here, there's just a lot of a values that we have to replace with 3. And then next we're going to have f triple prime of 3, and we're multiplying this by x minus 3 to the third over 3 factorial. And then this will continue on, but we could stop here because after the third derivative at 3, the pattern should be obvious. So now for the next step, we have to find f of 3, f prime of 3, f double prime of 3, and f triple prime of 3. And to get those terms, we're going to start off here with the function. We have f of x is equal to 1 over x plus 2. And the first thing I would do here is just rewrite this as x plus 2 to the negative first power. That way, when we take the derivative in a moment, we could just go ahead and use power rule. So we're going to have here next, we're going to have negative, and then x plus 2 to the negative 1 minus 1 is negative 2. Now, technically, we would have to use the chain rule here, but the derivative of the inside is 1. So writing times 1 doesn't change anything. So I'm just going to leave it out like this, and we'll just go to the next step. So now we're going to take the second derivative, and we're going to have negative 2 times the negative 1 in front is going to give us positive 2, and then we'll have x plus 2 to the negative 2 minus 1 is negative 3. And then for the next step, we'll have f triple prime of x is equal to, we'll have negative 3 times 2 is negative 6, and then x plus 2 to the negative 3 minus 1 is negative 4. So now let's find f of 3. So to get f of 3, we're just going to plug in 3 to f of x, and we'll have 1 over 3 plus 2, which is 1 over 5. And then for f prime of 3, we're going to plug in 3 to our first derivative. And what we'll have here is we'll have minus, and then 3 plus 2 is going to give us 5. And this is being raised to the negative second. So this is going to work out to negative 1 over 5 squared. And then for f double prime of 3, we're going to have 2 times 5 to the negative third. And this is just going to work out to 2 over 5 to the third. So we're just plugging in here and simplifying. And then for the next one, we're going to have f triple prime of 3 is equal to, we'll have negative 6, and then we're multiplying by 5 to the negative 4, and that's going to give us 5 to the fourth power down in this denominator here. So now for the next stage of the problem, we just plug in. So f of x is equal to 1 over x plus 2, and now this is equal to, we have f of 3 is equal to 1/5, and then we're going to have next plus f prime of 3, but that's equal to minus 1 over 5 squared. So I'm going to have minus 1 over 5 squared, and then we're multiplying by x minus 3. And then for f double prime of 3, we're going to have plus 2 over 5 to the third, and this is being multiplied now by, we have x minus 3 to the second over 2 factorial. But just know that 2 factorial is equal to 2 times 1, and that's equal to 2. So I'm just going to replace this denominator with a 2. And then next we'll have plus f triple prime of 3, which is minus 6 over 5 to the fourth, and we're multiplying f triple prime of 3 by, we have x minus 3 to the third power over 3 factorial. So we have x minus 3 to the third power over 3 factorial. But another thing to be mindful of over here is that 3 factorial is equal to 3 times 2 times 1, which is equal to 6. So we have 2 over 2 canceling, and then we'll have 6 over, once again, 3 factorial is equal to 6. So these terms will just cancel out. And remember, we could just keep plugging in terms here, but we'll just write plus dot 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 to imply that this will go on forever. So now let's clean this up a bit. We're going to have 1 over x plus 2 is equal to, we have 1/5 minus, and now I'm going to write this as a single fraction. We'll have x minus 3 over 5 squared. So this is over 5 squared. And then next we'll have plus x minus 3 to the second, and now we're dividing by 5 to the third power. And then for the next term, we have minus x minus 3 to the third power, and now we're dividing by 5 to the fourth, and then we just write our plus dot dot dot. So we just completed the first part of the question, but now we could write this in sigma notation. So we'll have 1 over x plus 2 is equal to the series going from n equals 0 to infinity. And now the first thing I notice here is that this is an alternating series, that the terms are changing sign one after the other. So I'm going to include a negative 1 to the n like this. And now be mindful here, we're starting off at n equals 0. So if I did negative 1 to the 0, that's equal to positive 1. And that's going to start us off here with the positive first term. And then what we have after is we have x minus 3 to the n power, And this is also going to be valid here because if I plug in n equals 0, I have x minus 3 to the 0, which is equal to 1. And then for my n equals 1 term, I would have x minus 3 to the first, and this would be my n equals 2 term. So things are looking good so far, but then the last piece that we have to account for is the denominator. And notice here that when we have a power 1, our power of 5 underneath is 1 greater. When we have a power 2, our power of 5 is still 1 greater. It's going to be 2 plus 1. 3 plus 1 gives us 4. So we're going to have 5 to the power n plus 1. So that's a small detail that we have to be careful of. But this would be our Taylor series expansion of 1 over x plus 2 centered at 3. Question 2, we're going to find the Taylor series for g of x equals cosine x about x equals pi over 2. So this is the center of our Taylor series. So we'll say a is equal to pi over 2. And we're going to plug this into the expanded part of the formula. So now our function is g of x. So we'll say g of x is equal to, and first we'll have g of a is g of pi over 2. And then we're going to tack on, we have plus g prime of a is going to be g prime at pi over 2. And we're multiplying this by x minus a. And once again, a is pi over 2. So we have x minus pi over 2. And now we just keep plugging into the formula. And we're going to have g double prime at pi over 2. And we're multiplying this by x minus pi over 2 squared. And we're dividing this part by 2 factorial. And then next, we'll have g triple prime at pi over 2. And then this will multiply by x minus pi over 2 to the third, and we're dividing this by 3 factorial. So then this will continue on and on, so we'll just write plus dot dot dot. So to write this Taylor series, we have to know what is g of pi over 2, what is g prime at pi over 2, g double at pi over 2, and g triple at pi over 2. So let's go ahead and find those pieces. G of x is equal to cosine x. And then we could find g prime of x, and that's going to be negative sine x. That is the derivative of cosine x. And then g double prime of x is going to be equal to negative cosine x. And then our third derivative, g triple prime of x, is equal to sine x. And then we could stop here because if we take a fourth derivative, if we find the fourth derivative of g, this is going to work out to cosine x. And notice that it brings us back full circle. We come back to cosine. So that's why we could stop at the third derivative. So now let's go ahead and plug in the center. So we have g of pi over 2, and that's going to be equal to cosine at pi over 2. And cosine at pi over 2 is equal to 0. And then we have g prime at pi over 2. That's negative sine pi over 2. And sine pi over 2 is 1, but with the minus in front, this is going to work out to minus 1. And then we have g double at pi over 2. And that's going to give us negative cosine pi over 2, which is going to give us 0. And then the third derivative of g at pi over 2 is equal to sine at pi over 2, which is equal to 1. So then if we were to find the fourth derivative here at pi over 2, this is going to bring us back to 0. And by now the pattern should be obvious. We have 0, negative 1, 0, 1, 0. The next value would be negative 1 if we were to take the fifth derivative at pi over 2. So now just plug into the formula. G of x is equal to cosine x. So we have cosine x is equal to g of pi over 2 is equal to 0. So we have 0 plus, and then the next term here, g prime at pi over 2 is minus 1. So I'm going to write minus, and we have x minus pi over 2 like this. And then our next coefficient is 0. G double at pi over 2 is equal to 0. So I'm going to have plus 0. And then after this, g triple prime at pi over 2 is equal to 1. So I'm going to have plus 1 times, we have x minus pi over 2 to the third power, and this is being divided by 3 factorial. So now the pattern might be obvious as to what's going on here. Notice that the only things that are making it, the only non-zero terms, are the odd powers here. Notice I have x minus pi over 2 to the first, then the third. So then the next one here will go to the fifth power. But another thing to be mindful of here is that the signs are alternating, that I have minus, and I have x minus pi over 2 to the first, and then I have plus x minus pi over 2 to the third. So my next one is going to be minus. My next non-zero term is going to be minus, and I'll have x minus pi over 2 to the fifth over 5 factorial, and this pattern will continue on and on. So now let's clean this up a bit. We could say cosine x is equal to, we have minus x minus pi over 2 first. So I'm just going to write the non-zero term. So we have this, and then the next non-zero term is going to be plus x minus pi over 2 to the third over 3 factorial. And then the next non-zero term, we have minus x minus pi over 2 to the fifth power over 5 factorial. And we could stop here, but if we were to write the next non-zero term, it would be plus x minus pi over 2 to the 7 over 7 factorial. So now let's write this Taylor series in sigma notation. So we're going to have cosine x is equal to, we have the series going from n equals 0 to infinity. And we have to notice here that this series is alternating. But one thing to be mindful of is that it's starting off negative. So if I say -1 to the n like this is not correct, because if I plug in 0, I get -1 to the 0 is 1, and that doesn't match the negative in front. So to fix that problem, I'm just going to write n plus 1. So now if I were to plug in n equals 0, I'll have -1 to the first, which is -1, and that will start us off here negative. So now we just have to think here, what's the pattern? Well, all the powers attached to these binomials are odd powers. So what we have is we're going to have x minus pi over 2 to an odd power. But we have to think carefully, how do we express an odd power for some integer value n? We're going to write 2n plus 1, because no matter what integer I plug in greater than or equal to 0, 2 times some integer greater than or equal to 0 plus 1 is always going to be odd. So this will express this entire series here. And you could even see that if we were to plug in n equals 0, so just something to think about, if you were to plug in 0 for n, you're going to have 2 times 0 plus 1. And that's going to start you off to the first power here. And if you were to plug in n equals 1, the next term, you'd have 2 times 1 plus 1, which would give you the power 3. And that's the next term that shows up in our series. So this is looking good, but now the next thing to consider here is that in our denominator, we have a factorial that matches the power above it. So we have a power 3 over 3 factorial. Then we have a power 5 over 5 factorial. So I'm just going to write 2n plus 1 in parentheses and throw the factorial on the outside. And now this is our Taylor series expansion for cosine x centered at pi over 2. Question 3, now we're finding the Taylor series expansion for h of x equals natural log x about x equals 1. And what's nice about this question here is that we can't find the Maclaurin series for natural log x. And the reason behind that, if we think about this, is that natural log x is not defined at 0. So if we had a center at 0, natural log of 0 is undefined. Okay, so this is undefined. So we wouldn't be able to find a Maclaurin series. And if we took the derivative of natural log x, which is 1 over x, and you go to plug in 0 here, you'd get 1 over 0. So once again, natural log x does not have a Maclaurin series, but we can find the Taylor series centered at 1. So now let's plug the center into the formula. So we're going to have h of x is equal to, and if we plug in 1 for our center, we're going to have h of 1 plus, and we'll have h prime of 1 times x minus 1. And then next we'll have plus h double prime of 1 times x minus 1 squared over 2 factorial. And then next we'll have h triple prime of 1 times x minus 1 to the third over 3 factorial. So now let's find h of 1, h prime of 1, h double prime of 1, and h triple prime of 1. So h of x is equal to natural log x. So that's our first thing we're writing down here. And then h prime of x, the derivative of natural log x, is 1 over x. And I'm going to write this as x to the negative first power, so that when we write our second derivative, h double prime, we could just use the power rule. So we're going to have -1 times the coefficient of 1 in front is going to give us -1, or just minus x to the -1 minus 1 is -2. And then next we'll have the third derivative is equal to, we're going to have -2 times -1 is +2, and then x to the -2 minus 1 is -3. So now we're ready to plug in the center. So we'll have h of 1 is equal to, we'll have natural log of 1, and that's equal to 0. And then h prime of 1, if we plug into our first derivative here, we're going to have 1 over 1, and that's equal to 1. And then h double prime of 1 is equal to, we'll have minus 1 to the negative second is 1, but with the minus in front, this is going to make h double prime of 1 equal to -1. And then we have h triple prime of 1. This is equal to, we're going to have 2 times 1 to the negative third, and that's just going to be equal to 2. Because remember, 1 to any power is equal to 1. So we're just writing down the coefficient here. So now we can plug into the formula here. We have h of x is natural log x, and this is equal to, we have h of 1 is equal to 0, and then we're going to have plus h prime of 1 is equal to 1. So we have 1 times x minus 1. And then next we have plus h double prime of 1, and that's equal to -1. So I'm going to have minus, and we have x minus 1 to the second over 2 factorial. But remember, 2 factorial is equal to 2 times 1, and that's equal to 2. I could also write next 3 factorial is 3 times 2 times 1, and that's equal to 6. And if I wanted to keep going here, I could say 4 factorial is equal to, I could even just write 3 factorial times 4, and that's going to work out to 24. So this is just going to help us write out the next few terms. So I have x minus 1 squared over 2 factorial is equal to 2. And then next we're going to have plus h triple prime of 1 is 2. And then we have x minus 1 to the third over 3 factorial is equal to 6. So 2 over 6 is going to reduce to a third. Now, if the pattern is not obvious up to this point, you could always find an additional term. So let's find our fourth derivative of h of x. And notice that I use this notation here. We have the 4 in parentheses. And that's because after your third derivative, you shouldn't write primes anymore. You should start writing numbers because it just makes it look a lot neater. So then to find our fourth derivative, we're going to do negative 3 times 2 is negative 6. X to the negative 3 minus 1 is negative 4. And now we're going to plug the center in. We're going to have the fourth derivative of h at x equals 1 is equal to negative 6 times 1 to the negative 4. And that's going to work out to negative 6. So then if we have this formula up here, notice that we stopped at this term here to the power 3. But if we had to continue this, we could say the fourth derivative of h at the center, so at 1, and then we would multiply by x minus 1 to the fourth over 4 factorial, and then this would continue on and on. So if we plug in the fourth derivative at 1 into the formula, our next term, we would have minus 6, and then we would multiply by x minus 1 to the fourth over 4 factorial. But remember, we said 4 factorial was equal to 24. So we'll just write that here, and then we would have plus, and this would continue. But notice here, 6 over 24 reduces to 1/4. So now we could clean this up a bit. We'll have natural log x is equal to, and we have x minus 1, and then we'll have next minus x minus 1 squared over 2, and then our next term will be plus x minus 1 to the third over 3, and then next we'll have minus x minus 1 to the fourth over 4, and this pattern continues. So now let's write our Taylor series in sigma notation. So we're going to have natural log x is equal to the series from n equals 0 to infinity. And notice that this is an alternating series. So we are going to have a negative 1 to the n here. And I'm using negative 1 to the n because we're starting off with a positive here. And we're starting at n equals 0. And then next we're going to have x minus 1 to the power. And this part here we have to be careful. We're not going to write the power n because notice that we're starting off here at x minus 1 to the first. So I have to include a plus 1 here, because notice that we're starting off at x minus 1 to the first. So if this is my n equals 0 term, 0 plus 1 would give me that power that we have right here. So we just have to be careful at this step. And then the next thing to notice here is that our denominator, the number in the denominator matches the power above it. So I'm just going to write an n plus 1 like this underneath. So this would be our Taylor series expansion for natural log x centered at 1. But before we move on, I just want to point out that there is another way we could write this series in sigma notation. We could say that natural log x is equal to the series from n equals 1 to infinity of negative 1, and in this case I can't say n, I would have to say m plus 1, because notice we're starting off positive here, and if I'm starting at n equals 1, negative 1 to the 1 plus 1 would start us at negative 1 squared, which is positive 1, which would once again start us off positive, which is what we need. So then next I would write x minus 1, and notice that I'm starting off with a power 1 here. So this time around, if I'm starting at n equals 1, then I could just write a power n above like this. And then my denominator matches my power above. So I have a power 2 and a denominator 2, a power 3 and a denominator 3. So in this case, I could just put an n underneath like this. So this would also be correct. Just know that when you are writing your Taylor series in sigma notation, there is more than one correct way to write it, but either of these two would check out. So now question 4, our last question, we're going to find the Taylor series expansion for w of x equals 2 to the x about x equals negative 3. So that's our a value. We have a equals negative 3. And the first thing we should do is plug that a value into the expanded part of the formula. So we're going to have w of x is equal to, and our center is at negative 3. So we have w of negative 3 plus we have w prime at negative 3. And for this part, we just have to be careful. We have x minus a is equal to minus 3. So we have minus 3, and that's going to change to a plus 3. So just be careful here. Don't do something, some students sometimes will just write x minus 3. But this is a very dangerous bear trap. Just know that when you have a center that's negative, your signs are going to be different here next to your function input and the binomial next to it. So just be mindful of that. So now the next term here, we're going to have plus w double prime at negative 3, and then this will be multiplied by x plus 3 to the second over 2 factorial. And then for our next term, we have w triple prime at negative 3, and this is multiplied by x plus 3 to the third over 3 factorial. And then after this, we'll be able to see what the pattern is. So we'll just stop here and just say that this will continue on and on. So now for the next part of this question, we're going to find these 4 terms here, because that's going to tell us the coefficients of our Taylor series. So these 4 terms we're going to find by starting with w of x, which is 2 to the x power, and we're going to start taking derivatives here. So we have w prime of x is equal to the derivative of 2 to the x power is 2 to the x times natural log 2. And now for our second derivative, we're going to use the constant multiple rule for derivatives that we have natural log 2 times 2 to the x. So when we take the derivative of this function, we're going to leave the natural log 2 alone, and then we're going to take the derivative of the 2 to the x part, and that's going to be 2 to the x times natural log 2. So now we have natural log 2 times natural log 2, and that's going to make, we're going to have 2 to the x times natural log of 2 squared. So this pattern will continue. We're going to have our third derivative is equal to, we have 2 to the x, and now we're going to have natural log of 2 to the third power. So now we're ready to find these four terms, but let's go ahead and give ourselves a little bit of space here. So we're going to have, when we plug in, we have w of negative 3, and this is equal to, we have 2 to the negative third, and that simplifies to 1 over 8. And then for w prime, we have w prime at negative 3 is equal to, we'll have natural log 2 times 2 to the negative third, and that's going to give us natural log 2 over 8. And then for our second derivative, we're going to have w double prime at negative 3 is equal to, and when we plug in negative 3, we're going to have natural log of 2 in parentheses squared over 8. And now for our third derivative, we have w triple prime at negative 3. This will be equal to, we'll have natural log of 2 to the third power over 8. So now let's plug everything in. We have w of x is equal to 2 to the x power, and this is equal to w of negative 3 is 1/8, and then we're going to have plus w prime at negative 3 is natural log 2 over 8, and then this is being multiplied by x plus 3. So we have x plus 3 here, and then next we have w double prime at negative 3 is natural log of 2 in parentheses squared over 8, and this is being multiplied by x plus 3 to the second over 2 factorial. So we have this here. And then for our next term, we have plus natural log of 2 to the third over 8. We're just replacing this w triple prime at negative 3. And then this is going to be multiplied by, we're going to have x plus 3 to the third over 3 factorial. And then we just write plus dot 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 to show that this is going to go on forever. So now for our last step, we're just going to write this in sigma notation. We have 2 to the x is equal to the series from n equals 0 to infinity. And we have a 1/8 attached to everything. And then notice that everything has a natural log 2 being raised up to a power. So I'm just going to write here, we have natural log 2, and we have to be very careful with which power we choose, but we're going to use the power n, because if we're starting here at n equals 0, natural log of 2 to the 0 power is 1, and that's going to start us off at the 1/8. And then notice that we have an x plus 3 next to it. So we have x plus 3, and the power of x plus 3 matches the power of natural log 2. So we're just going to write an n over here like this. But then the next thing to be mindful of is that underneath it all, we have a factorial, and the factorial matches the power above it. So when we have a power 2, we have a 2 factorial. When we have a power 3, we have a 3 factorial. So I'm just going to write an n factorial underneath like this. And this is the Taylor series expansion for 2 to the x centered at negative 3.